Okay, make sure you download the app introduction. Keep reading over and over. That maybe will be helping you to understand about the radio frequencies. Okay, so now you can see that will be electromagnetic spectrum from 30 Hz to 300 gigahertz. So they're telling you, which one. ELF, VF, VLF, that means from what frequency to what frequency. Okay, LF, MF, SF, VSF, USF, and so on. Okay. High frequency, that means from 3 megahertz to 30 megahertz. Very high frequency, 30 megahertz up to 300 megahertz. Ultra high frequency, 300 megahertz up to 3 gigahertz. Super high, okay, 3 gigahertz up to 30 gigahertz. And the last one, extremely high, 30 gigahertz up to 300 gigahertz. That they give you electromagnetic spectrum above 300 gigahertz. Okay, so you can see they can be listing in here for you. Frequency and wavelength. This is a very basic definition. Everyone learning electronics supposed to remember. What is a cycle? One complete occurrence of repeating wave periodic signal, such as one positive, one negative alternation of a sine wave. That will be one cycle. What is the frequency? Frequency, the number of cycles of a signal that occur in 1 second. Period, the time distance between two similar points on a periodic wave. And the last one, wavelength, the distance traveled by electromagnetic or radio wave during one period. That one you already learning in the filter. Okay. First one filter section. You understand one filter section. That means when you increment the cutoff frequency, okay, 10 times, they're going down 20 dB. That one choose sections. That means you are to C, they're going down 40 dB. 3 sections, okay, and 4 sections. That means 6 or 8, okay. And that one we already showed you before. Okay, different frequency. Okay, different filter designed by different engineer. Okay, and if you're looking into this display here, you're able to tell which filter will be better. And if you're looking into here, this is just the ripple, the noise. Okay, so we already know from this one look like the best will be best sell. Why? First thing, they have a no noise, okay, in the mid range, and also they will be close to the cutoff. And the second one, you can see, let's see, but the words, okay, there will be no noise in the mid range here. However, they will be far at the cutoff than the best sell. Okay, then you can see elliptical, they get a very good for the cutoff, very close to the cutoff frequency. However, they get the noise. Okay, they get the noise. That's what we don't want it. And temperature, okay, very good for the cutoff. However, they still get the noise. That's what we don't want it. On that one here, basically you try to understand the thing is when you interview for technician job, easy for them to asking you, okay? And that will be telling you the relation between the sideway and the square way. You understand it is sideway, okay? You can get a fundamental frequency and you can get a different, okay, frequencies, okay? And when you're looking into here, you can see this is the fundamental, okay? And the next one will be third harmonic, okay? If I telling you, if the fundamental of the sine wave is 1 kilohertz, so what is the third harmonic? How many hertz? You tell me how many hertz for third harmonic. Who can carry me? That's what on the AC we already talked to you. You get a third harmonic and you get, okay, fifth harmonic and so on. So if you understand what the frequency for third harmonic, then you can understand the frequency for fifth harmonic and seventh harmonic and so on. we're not using the even harmonic. So if the base fundamental frequency 1 kilohertz, and third harmonic will be 3 kilohertz. Fifth harmonic will be 5 kilohertz. Seven will be 7 kilohertz. And that will be telling you too many harmonic of the sine wave given you the sine wave. Okay? A square wave. So the square wave will be combined at too many harmonic of the sine wave. And now, before we can moving on, I want to know the bandwidth. What is the definition for the bandwidth?
F2 minus F1.
Okay. Question will be bandwidth of 1 kilohertz. Sine wave. Okay, what is the bandwidth of 1 kilohertz sine wave?
0.
Perfect. Now, the definition for the bandwidth. That means the difference between F maximum minus F minimum. For 1 kilohertz sine wave, so the maximum and the minimum still 1 kilohertz. Okay, so the bandwidth of the 1 kilohertz sine wave will be 0. Then 1 kilohertz minus 1 kilohertz, you get a 0. However, if they're asking about the bandwidth of the square wave, that's a difference. The thing is the square wave will be combined too many sine wave. Fundamental, third harmonic, fifth harmonic. Okay. So the bandwidth of the fifth harmonic of square wave can you tell me what's the bandwidth of the fifth harmonic of the square wave? F maximum, F minimum. What bandwidth equal? Of 1 kilohertz. What the bandwidth equal? They will be equal F maximum minus F minimum. You know, minimum will be 1 kilohertz. That's the fundamental. And the fifth harmonic, that means 5 kilohertz. 5K. The answer will be 4. So depending on what the harmonic they want. Normally for the technician, you will be calculate up to 13 kilohertz only. We don't care more than that. Complex waveform. Okay, complex waveform is any signal that is not a sine wave. It can be a square wave, triangle wave, sawtooth wave, human voice, music, or digital data. That will be complex waveform. Any periodic signal that is not a pure sine wave can be considered to be built out of the following components: a DC component or average, which can be 0. A fundamental sine wave that has a frequency exactly the same as the frequency of the signal. An infinite number of harmonic. Harmonic is a frequency that is exact multiple of the fundamental frequency. Note, in perfect square wave, there are an infinite number of frequencies present. We only need to analyze up to 13 harmonic in order to get a decent reproduction of a square wave. That's what they're telling you. Okay? That means if you're working on a square wave, the maximum harmonic, we can go up to 13. They can go 13, 15, 17, and so on. However, they want only up to 13 for any calculation. Okay, now you can see this is the square wave. Will be displayed on oscilloscope. 3 of 1 kilohertz sine wave. However, this is the time domain. Okay, time domain. And now, when they display on the spectrum analyzer, Spectrum analyzer, that means frequency domain. It's a kilohertz. So the same square wave. If you're looking at the spectrum analyzer, you can see this is a fundamental frequency of 1 kilohertz. They're telling you 1.27 VP. And then 3 kilohertz. Third harmonic, they just telling you, you get 424 millivolt peak. Fifth harmonic, you get 255 millivolt peak at the 5 kilohertz. 7 kilohertz, and they just telling you, you get 182 millivolt peak. Okay, so you can see the two different. This is the time domain. That means display on oscilloscope. You can see only one side wave, one square wave, one square wave with the frequency 1 kilohertz. So that's why the period will be 1 millisecond. However, for spectrum analyzer, there will be a frequency domain vary with the frequency. They do not see any square wave. However, they're telling you square wave at the 1 kilohertz. What is the amplitude of this signal? 3 kilohertz, 5 kilohertz, 7 kilohertz, and so on. Okay, so now basically you can see the difference between oscilloscope and the spectrum analyzer. Oscilloscope will be cheaper, maybe 1,000, 2,000, 3,000. You can buy oscilloscope. However, for spectrum analyzer, what we get is 24,000. Okay. It is the same thing. Okay. It is a square wave in the time domain. That means in the scope. Okay. However, same signal display on the spectrum analyzer. You can see 1 kilohertz, what the value. Okay, 3 kilohertz, and so on. 11 kilohertz, 17 kilohertz. Okay, they're just telling you what the amplitude. Square wave oscillator. You understand what that means? What is the square wave oscillator? If you're going to buy the oscillator, 1 kilohertz square wave, when you turn on power, automatic, they just given you square wave, 1 kilohertz. Okay, and this is the band pass filter. You understand the band pass filter? Okay, that means they allow the signal between the lower cutoff. That means higher lower cutoff and less than higher cutoff to pass any different frequency will be locking. This is a band pass filter 3 kilohertz. That means any frequency inside 3 kilohertz, they can go. Otherwise, they will block it. This is a fundamental block out. Okay, so basically this is a 3 kilohertz. So only the signal, okay, in lower cutoff, higher cutoff allow to pass. Okay, any signal out of that range will be blocking. That's what you can see, okay, in the spectrum analyzer. Electronic communication is everywhere. WhatsApp, TV broadcast, or listen to the radio. Use telephone, use remote control, and more. Okay? Electronic system. A system can be defined as a group of components that work together to complete a job or a task. Okay? A subsystem is just a part of a system. It helps to complete a task. A subsystem is often shown in the block diagram. Now, you can see that one. They're talking about the radio system. This is a microphone. When you're talking to the microphone, okay, your voice could be a sound wave. When they go through the microphone, they convert to the electrical wave. Okay, then they can be using the amplifier to amplify that signal. Okay, then that signal will be go to the amplifier, then go to antenna, so the signal can transmit it over the air. That we're talking about transmitter. Okay, and this one here is receiver. That means your radio. Your radio antenna here. Okay, you get signal go to the voltage amplifier and go to the power amplifier and go to the speaker. This is receiver. That's two things you need to know. One will be for transmitter and the other one for receiver. Okay, a microphone is a type of transducer. It's converting pressure variation in a sound wave into electrical energy. That's what I just talking to you. When you're talking to the microphone, they're converting the sound wave to electrical wave. A transducer is any device, okay, that converting one form of energy into another. The transmitting antenna converting amplify information signal into a new form. The transmitting antenna, okay, will be convert the amplified information signal into a new form of energy capable to traveling through the space. This new energy is called electromagnetic energy or radio wave. Electromagnetic energy consists of two fields, a voltage or electric field and a magnetic field. It travels through the space at the speed of light, which about 3 times 10 power of 8 meter per second. When meeting antenna requirement. Radio transmitting antenna need to be at least 1/4 of wavelength long. Okay. Audio frequency are those we can hear. They are from 20 Hz up to 20,000 Hz. An audio frequency, okay, that is in the middle of the out hearing range is 1,000 Hz or 1 kilohertz. Okay, let's calculate the wavelength of 1 kilohertz electromagnetic wave. Okay, lambda equal V divided to F. You take the speed of light 3 times 10 to the power 8 meter per second divided 1 kilohertz. You get 300 kilometer. Okay, antenna need only 1/4 of this distance, or 75 kilometer. Increase the frequency always decrease the wavelength. Decrease the frequency always increase wavelength. Let's try changing from 1 kilohertz to 10 kilohertz. Then lambda equal 30 kilometer, and the length antenna will be 30 divided 4. They will be 7.5 kilometer. If frequency equal 150 megahertz, then lambda equal 2 and meter, and L antenna will be equal 2 divided to 4. You get 0.5 meter. So at higher frequency, then the antenna long will be shorter. Okay, modulation. 150 megahertz signal may transmit just fine. But there's one more problem. We can not hear 150 megahertz. Okay, that means you get a frequency high signal. It's okay to transmit it. However, you could not hear. Okay, it is too high in frequency. This is a solution. It's called modulation. Okay, when we modulate a wave, we place a low frequency information signal onto it. The low frequency signal is just a long for the ride. It is in effect carrier on top of the signal frequency signal. The high frequency signal is therefore called carrier signal. Okay, so basically, the signal at a high frequency, they can transmit easy over the air. However, you cannot hear on that high frequency. So your voice, very low frequency, in order to transmit over the air, you need a signal they call a carrier. That means that signal get a high frequency, try to carry your voice, okay, over the air. Many mobile FM radio units operate near 150 megahertz. At this frequency, wavelength calculation equal to meter and L meter, the long of the wavelength lambda divide 4, you get 19.7 inches. Frequency above the range of hearing are called radio frequency. Any frequency above 20 kilohertz is considered a radio frequency. Okay, and now this is an example, and I already told you how do we calculate it. What is the wavelength of a 710 kilohertz AM broadcast signal? What is the minimum height of the antenna tower in feet if it is 1/4 of a wavelength long? So you can calculate the wavelength, take a V divide X, okay? You get 420.5 meters, okay? And the length will be lambda divide 4, given to you 346.6 feet, okay? Next example, a square wave, lambda divide 4, with antenna measure 108 inches. What is the approximate operating frequency of the transmitter? Okay, so basically you take a lambda divide 4, you get the 2.74 meter. The wavelength is 4 times lambda over 4. That given you 10.97 meter. And F will be equal to V divided to the lambda here. You get 27.3 megahertz. That will be just example regarding into the antenna. There are 3 ways we can impress information onto a carrier. We change the voltage or power of the wave in the step with the information. This is called amplitude modulation. Okay, that means you change the amplitude of the signal. We can alter the frequency of the wave with the information. It is called frequency modulation. And next one will be change the phase. That's what they call PM. Okay, phase modulation. So you get 3 ways to transmit it. You can use AM modulation or FM modulation or PM modulation. AM modulation, you change the amplitude. FM frequency modulation, you change the frequency. And PM modulation, you change the phase. Okay, practical radio system. Every radio transmitted is assigned to operate on a specific carrier frequency. The job of the carrier oscillator is to generate this frequency. The purpose of an oscillator is to convert the DC from power supply into AC signal. The output of the carrier oscillator is a nearly clear sine wave. The modulator has two inputs. The radio frequency sine wave from the carrier oscillator, the information signal. The output of the modulator is a modulated carrier wave. Okay? So you get two things. You get the signal from your voice. And also, you can get the carrier signal coming out from oscillator. Section 6 point. What is the purpose of an oscillator circuit? What they said, the job of carrier oscillator is to convert DC from power supply into an AC carrier frequency. Number 2, how does an RF amplifier different from AF amplifier? RF is non-linear amplifier and audio AF linear. So basically you get two different amplifiers. One they call RF, one they call AF. If you already learned the type 1 electronic, you know you can get the amplifier, differential amplifier, inverting amplifier, non-inverting amplifier, and so on. On that amplifier, if you want to change the gain, you must be change the value of the resistor. Okay? However, RF is a non-linear amplifier. That means you don't have to change anything. Automatically, they given you the gain. That is the difference between RF and AF amplifier. What is the purpose of modulator circuit? The purpose of modulator circuit is combine carrier oscillator and the information, that means your voice, to produce a modulated carrier wave. Okay? So that is the purpose for the modulator. Okay? How many radio signals can be placed in the antenna circuit of the receiver? That means in your radio. How many signals ready for your antenna? The answer will be 1,000 signals. Too many signals. Okay? How does a radio receiver select one signal from 1,000? The answer will be LLC resonance circuit at the band pass filter. This filter is tuned to the free carrier frequency of the transmitting station. That's why when you tuning your radio, that means you're looking on the signal frequency you want. They're using LC resonance circuitry. Okay? What happened in the detector circuit? It takes the incoming modulated carrier wave and strip away the carrier frequency, leaving a copy of the original information. Okay, that means when you tune into the station you want, okay, then they can be stripped away and a different not frequency you're looking for. Okay. AM modulation. This is a home picture block diagram for AM modulation. This is the first one, AM modulation. This is your voice right here. They go to the microphone, they go to the amplifier. The reason they need the amplifier, the thing is, your voice, the signal will be very, very weak. They cannot be working in the circuitry. So that's why they need voltage amplifier. And that they go to the modulator. And the modulator get another oscillator they call RF carrier oscillator. So the modulator can be get two signal. One signal from your voice and one signal from carrier oscillator. So they combine the modulator signal here, go to RF power amplify, then go to antenna to transmit it. Okay, on the second one, receive for this will be transmitter. That will be receiver. That means your radio. Okay, that just tells you practical radio system. In radio, your radio, you get antenna. Okay, too many signal transmitted here. However, when you changing LC, that means you select the frequency you want. Go to the what we call band pass filter. Okay, and after you get the signal you want, they go to RF amplifier. And now they go to detector, the modulator circuitry. And after that, they go to power amplifier and go to the speaker. That's just a very, very basic block diagram for the radio, for transmitter and receiver. So you have to memorize this block diagram. Okay, then we can see for transmitter, RF carrier oscillator in output, your voice output go to the circuitry. That's what we call a modulator. And after the modulator combine carrier and your voice, they're coming out. And they need the power amplifier to make it stronger before they can be transmitter. And the receiver, you get the antenna, and in antenna here, you get too many signals. However, you can tune in your radio by changing LC to select the frequency you want, and that have to be amplified. And also they have to be go to detector, the modulator, then amplify again before they go to the speaker. Okay, making an AM signal. You can see in here, this is the oscillator. You have to understand oscillator. You can go to buy oscillator 1 megahertz. When you connect power, the signal coming out at 1 megahertz. Okay, that means different oscillator, you can get different frequency. So that's why when you want to buy the oscillator, they will be asking you what frequency you want. And another one in intelligent input, that means your voice. Okay, carrier coming in, your voice coming in. Inside, that's what they call modulator amplifier. Okay, and after they done here, they're coming out amplitude modulated output. Now, the first step in any transmitter is an oscillator. RF carrier wave contain no information until it is modulated. Okay, that means basically oscillator, they just given you what frequency. Okay, in order for amplitude to be changed, the voltage or the power gain of a subsequent state must be changed. The AM generator has a special amplifier with a variable voltage gain we call a modulator. That means inside here, they automatically changing the signal, changing the gain. Okay. The amplifier with a constant gain equal a linear amplifier. The variable gain amplifier is a non-linear amplifier. So like we already talked to you. Okay, linear amplifier, like inverting amplifier, non-inverting, summing amplifier. You want to change the gain, you have to change the resistor value. And a non-linear amplifier, that means you don't have to change anything. Automatically, they change the gain for you. A non-linear amplifier is always required to generate AM. That means inside here, you get an amplifier, non-linear. So they automatically changing the amplitude of your voice, your signal. What is the information? In AM signal, the information is carried on top of RF carrier. That means the carrier will be carry your voice on the top. Okay. The actual shape of the carrier is altered by addition of the information during the process of modulation. The imaginary lines that make up this shape are called the envelope. The envelope is a copy or duplicate of the intelligent signal. Percentage of modulation and AM modulation index. In AM signal, the percentage of modulation is measure of how strongly the carrier wave is being changed by the information. For radio, the higher the percentage of modulation, the louder the signal will be in the receiver loudspeaker. The variable gain amplifier is a non-linear amplifier. That means you don't have to do anything. Automatically, they change. That will be non-linear. A non-linear amplifier in own way required to generate AM signal. The maximum percentage of modulation is 100%. A 0% modulation means that no modulation is taking place. The transmitter is said to be dead key or unmodulated. The AM modulation index is the same information as the percentage of modulation. It is given simple M, small letter m, and can have a value between 0% modulation, okay, and 100% modulation. When calculate the percentage of modulation in an AM signal, we are really calculate the modulation index. Remember that the maximum modulation index is 100%. A signal that is over 100% modulated is said to be over modulated, which is an illegal condition. Over modulation distorts the information and cause excessive bandwidth to be used by the transmitter. Example: what percentage of modulation corresponds to a modulation index M of 0.5? Okay, percentage modulation will be 100 times 0.5. You get 50%. Definition and measurement of modulation index. AM modulation index can be defined by the formula. M will be equal to Vm divided Vc, where Vm is the information voltage and Vc is the carrier voltage. Okay, to measure the modulation index on an oscilloscope, use the following: M equal V max minus V minimum divide V max plus V minimum. If you're looking in here, okay, this is a signal. Okay, in here, your voice here, okay. Inside here, that will be the frequency, okay, to carry your voice. When they transmit it, they get both sides identical. And that's what they call carrying you. V minimum here. And that will be the maximum. That is a maximum. Okay? And that will be minimum. So M will be equal to V max minus V minimum divide V max plus V minimum. When you're looking, this signal will be displayed on the oscilloscope. That will be telling you what the V max, okay, and what is the minimum. List 3 application of AM. First thing, local broadcast, aircraft communication, software broadcast in SFS. Why are FM and PM have to observe on an oscilloscope? They claim since the information is 1 kilohertz and the carry a 1 megahertz. That means 1,000 kilohertz and 1,000 cycle of carrier plates for every cycle of information. Since the oscilloscope is adjusted to show 1 cycle of information, it also sees 1,000 cycles of carrier. The carrier sideway blend together, forming a solid figure. Okay, what instrument is preferred to measure FM and PM signal? That they're telling you, you better using spectrum analyzer. Why does the variable gain amplify state in the next generate AM? When the information goes positive, the amplified gain increase. This causes the output voltage AM signal swell or grow in amplitude. The opposite happens on the negative half cycle of the information. The AM signal sink in amplitude because the amplitude gain has decreased. Okay, a non-linear amplified star is required to generate the AM. Okay, I recommend you want to know about RF. You have to this is a document I prepared from different textbooks, and that will be very, very good. You have to reading over and go to the example, go to the section checkpoint, then hopefully you can get better understand. Now, this is a signal coming out of modulator. First thing, in this signal here, you get 2 signals. One will be your voice, and one will be carrier. Okay? This is your void right here. This is your void. And the frequency inside here, that's the carrier frequency. Okay? This is the carrier frequency. And they telling you, okay, we make data amplitude, okay, and also the minimum. Just talking about the amplitude, and this goes from this side to this side will be peak to peak, okay. The thing is, on the generator, on the modulator, when you get the signal carrier and your void, automatically they create both sides. Okay, they will be the same thing. Now, suppose that an AM signal we make peak to peak value read from gratitude on the oscilloscope screen is 5.9 division, and V minimum peak to peak 1.2 division. They want to calculate the modulated index, okay, and Vm, okay, equal V max peak to peak minus V minimum peak to peak divided by 2. You get 4.7. The fourth one, you get 7.1. And now suppose that an AM signal on the oscilloscope is so. An oscilloscope setting 1 volt per division. They want to know the modulated index. Okay? You have to know what is the modulated index. Okay? VC, how many volt? VM, how many volt? You see that? VM equal V max minus V minimum. Okay? Divided by 2. Now you can count 1, 2, 3, 4, 5, 6. That's the maximum. The minimum will be 1. This is a minimum. 1 joule. 6 minus 2 divided by 2. So V carrier 4 volt and V M 2.0 volt. And if you want to calculate the M in that, take VM divided VC, you get 50%. This will be displayed on the oscilloscope. Okay, same thing. Okay, now this is the signal. Okay, and they said 100% modulation, and this is over modulation. Now, if you're looking in, compare between this and that one, okay, you can see that one here and going up, but that one is different. You can see here. That's what they call over modulation. The intelligent voltage is too large for the carrier. First, the envelope is no longer an accurate copy of information. Second, excessive bandwidth that will interfere with adjacent stations. Okay. Remember, this is your point. Okay. And basically, this is just a little here, but not as long here. That's what they call over modulation. Frequency domain AM analysis. In this domain, it's easy to measure the bandwidth and the total power of the AM signal. So this will be displayed in the, let's see, in the frequency domain. That means they display in the spectrum analyzer. Okay. The 100 kilohertz carrier modulate 5 kilohertz information. That will be telling you your voice 5 kilohertz. And they get a carrier 100 kilohertz. Okay. This shows on spectrum analyzer. 100 kilohertz here. Okay, carrier. And they tell you carrier frequency. That's what you get 10 volts. Okay. And your voice 5 kilohertz. That means this is lower. Okay. That means 95 kilohertz. Your voice here will be 5 kilohertz. And this will be upper. Okay. Upper sideband or upper side frequency. And the other side will be lower sideband or lower side frequency. Okay. You can see this signal on the spectrum analyzer. Okay. You can see one upper sideband and one lower sideband. The thing is your voice 5 kilohertz. This is a carrier. Okay. Okay, frequency domain revised. Figure 3.10. Let's see. 3.11. Okay, that's what they talking about 100 kilohertz. Sideways in the frequency domain. How do we know this is a sideways since there is only one frequency present, 100 kilohertz. The sideways is the only pure waveform and it contains only one frequency. What happened when this carrier signal is amplitude modulated? In the frequency domain, the rapidly changing amplitude show up at a new frequency called a sideband. Sideband are a new frequency generated during process of modulation. They are created by non-linear distortion introduced by modulator amplifier. All modulation create sidebands, whether it be AM, FM, or PM. Suppose that 100 kilohertz carrier AM liquid modulated by a 10-volt 5 kilohertz information signal. The resulting frequency domain picture will look like figure 311. Okay, that means 311 here. What are the sidebands? The 5 kilohertz information signal seems to have disappeared in the display. In reality, the information energy 5 kilohertz had been transformed into sideband energy 95 kilohertz and 105 kilohertz. The sideband contains the information. Okay, frequency upper sideband FC plus XF. Lower will be FC minus FM. So that's why you can get 95 kilohertz and 105 kilohertz. Okay. The 100 kilohertz carry modulated by K. That's what we already showed you. Carrier 100K. Your voice will be 5K. So this is lower, and this will be upper of the band. V upper sideband, V lower sideband equal V M divided by Joule. Example, calculate the bandwidth and modulation index of the AM signal. So that means this one here. Bandwidth equal F maximum minus F minimum. That means you take 105 minus 95. You get 10 kilohertz. M will be equal ratio between Vm and Vc. Vc equal 10 volt. Vm equal Joule times V upside band. Okay. Joule times, I think, V lower sideband equal to 1. That means Joule times 1 over Joule. For AM signal, so in this figure here, .12 here. Calculate the following. the information frequency, FM. The voltage in the upper sideband, the bandwidth, ampersand of modulation. If they given you this signal, okay, this display here, F carrier, okay, equal F upper sideband minus FM. Then FM equal F upper sideband minus carrier. This is a carrier here, 810 kilohertz. This is the upper. That's easy to recognize. You take upper minus carrier, okay? Then you get 3 kilohertz. V upper sideband and V lower sideband. Okay, they want to know what voltage here. They will be the same. Okay, will be equal 5 volt. Bandwidth, F maximum minus minimum, F minimum. Okay, F upper sideband minus F lower sideband. Okay, since FM 3 kilohertz, then F lower sideband equal FC minus FM. Okay, equal 807 kilohertz. Bandwidth equal F upper sideband minus F lower sideband. You get 3 kilohertz. You understand 3 kilohertz here, 3 kilohertz here. So that will be the bandwidth. M equal Vm divided Vc. Vm equal to time V upper sideband divided to V lower sideband. 2 times 5, 10 volt. And M equal 50%. Make sure you have to go through the example. That can, if you can do until you don't have to see the solutions, that means you're able to understand. Another example here. AM signal have the following characteristics. VC 100 volt, 100 volts. FC 2182, carrier frequency, and VM 25 volt. Okay, FM 2.5 K. Okay, let's see. What is the bandwidth? Bandwidth equal to FM. That means 5 kilohertz. This is the bandwidth. M equal VM divided VC. 25 divided 100. That means you get 0.25. To draw the spectrogram, we modify the sideband frequency and the voltage. Okay, V upper sideband equal V divided V lower sideband equal VM divided 2. 25 divided 2. Okay, you get 12.5 volt here. Okay, F upper sideband, FC plus FM, F lower sideband, FC minor. Okay, so that given to you. This is the upper sideband and this is lower sideband. Okay, so today I will be stopped here. Okay. After the next week, we will try to finish that thing. Okay. If you don't not interesting, you don't have to be in the Zoom. Okay. I just try to help any student want to know about the IF. So any question, let me know. Okay. What I recommend to you, try to go through this handout over and over. They will be helping you to understand the signal, radio signal transmitted over the air. And the signal will be enter your radio. We're talking about transmitter and also receiver. Okay, anything else? I can help you. Okay, no question? I will be working on try to see any take one student able to get a certificate and move to the Tech 2. Okay, and any student Tech 1 still in Tech 1 for the fall 2023. We'll let you guys know. Also, one student asking me about the Tech 1 certificate. We already did it. However, we have to ask them what happened. How come up until today we still not get the certificate? Okay, we'll let you guys know as soon as possible. Okay, if it's no question, anything. Good night, everyone.
Good night.
Good night, sir.
Good night.